Hey math fans! Welcome to Math Olympiad Academy, your trusted space for advanced problem solving and logical reasoning. We sincerely thank our subscribers and all viewers for your continued support. In Lesson 30, we solve a second-order linear differential equation step by step using the method of undetermined coefficients, a systematic technique for constructing particular solutions. By applying initial conditions, we then determine the unique solution to the differential equation. The objective of this lesson is to solve second-order linear, non-homogeneous, ordinary differential equations with constant coefficients using the method of undetermined coefficients, and to determine the unique solution when initial conditions are given. In this problem, we aim to solve the following second-order differential equation: 2 times the second derivative of y with respect to x, minus 3 times the first derivative of y with respect to x, minus 2 times y of x, equals 3 times e raised to the power of minus 5x. The initial conditions are y of 0 equals 0, and the first derivative of y with respect to x at x equals 0 also equals 0. To solve this linear second-order differential equation, we begin with its associated homogeneous differential equation, obtained by setting the right-hand side equal to 0. That is, we solve 2 times the second derivative of y with respect to x, minus 3 times the first derivative of y with respect to x, minus 2 times y of x equals 0. To solve this homogeneous differential equation, we assume a solution of exponential form. Y of x equals e raised to the power of r times x, where r is a constant to be determined. Since y of x equals e raised to the power of r times x, the first derivative of y with respect to x equals r times e raised to the power of r times x, and the second derivative of y with respect to x equals r squared times e raised to the power of r times x. Substituting these expressions into the homogeneous equation gives 2 times the quantity r squared times e raised to the power of r times x, minus 3 times the quantity r times e raised to the power of r times x, minus 2 times the quantity e raised to the power of r times x, equals 0. Factoring out e raised to the power of r times x from all terms yields the quantity 2r squared minus 3r minus 2, all multiplied by e raised to the power of r times x, equals 0. Since e raised to the power of r times x is never 0 for any real number x, we divide both sides of the equation by e raised to the power of r times x, which gives 2r squared minus 3r minus 2 equals 0. This algebraic equation is called the characteristic equation. Now, let us solve the characteristic equation using the discriminant delta method. The equation is 2r squared minus 3r minus 2 equals 0. This is a quadratic equation in the canonical form. A times r squared plus b times r plus c equals 0. In our case, a equals 2, b equals negative 3, and c equals negative 2. The discriminant delta is b squared minus 4 times a times c, which equals 9 plus 16, giving delta equals 25. Since delta is positive, we have 2 distinct real roots. Applying the quadratic formula, r equals negative b plus or minus the square root of delta all over 2a. This gives r sub 1 equals the quantity 3 plus the square root of 25 all over 4. Since the square root of 25 is 5, this becomes the quantity 3 plus 5 all over 4, which equals 8 over 4. So r sub 1 equals 2. Likewise, r sub 2 equals the quantity 3 minus 5 all over 4, which equals negative 2 over 4. So r sub 2 equals negative 1/2. Now, in step 3, we write the general solution of the homogeneous equation. Because we have two distinct real roots, r sub 1 equals 2 and r sub 2 equals negative 1/2, the homogeneous solution is a linear combination of the corresponding exponential functions. That is, y sub h of x equals c sub 1 times e raised to the power of 2x plus c sub 2 times e raised to the power of negative x over 2. Here, c sub 1 and c sub 2 are arbitrary real constants to be determined later if initial conditions are provided. Now, in step 4, we find a particular solution to the non-homogeneous equation. The right-hand side of the original second-order differential equation, that is, the equation 2 times the second derivative of y with respect to x, minus 3 times the first derivative of y with respect to x, minus 2 times y of x equals 3 times e raised to the power of minus 5x, is 3 times e raised to the power of minus 5x. Since minus 5 is not a root of the characteristic equation, we use the method of undetermined coefficients. This method assumes a particular solution of the form y sub p of x equals alpha times e raised to the power of minus 5x, where alpha is an unknown constant to be determined. Now, let us differentiate the particular solution and substitute it into the original differential equation. We have y sub p of x equals alpha times e raised to the power of minus 5x. Its first derivative is minus 5 alpha times e raised to the power of minus 5x. Its second derivative is 25 alpha times e raised to the power of minus 5x. Now substitute these expressions into the left-hand side of the original second-order differential equation. 2 times y double prime sub p minus 3 times y prime sub p minus 2 times y sub p. This gives 2 times 25 alpha e raised to the power of minus 5x minus 3 times minus 5 alpha e raised to the power of minus 5x minus 2 times alpha e raised to the power of minus 5x. Factoring out alpha times e raised to the power of minus 5x, we obtain the quantity 50 plus 15 minus 2, all multiplied by alpha e raised to the power of minus 5x. Since 50 plus 15 minus 2 equals 63, this becomes 63 alpha times e raised to the power of minus 5x. The right-hand side of the equation is 3 times e raised to the power of minus 5x. So we have 63 alpha times e raised to the power of minus 5x equals 3 times e raised to the power of minus 5x. Now, since e raised to the power of minus 5x is never 0 for any real x, we may divide both sides of the equation by e raised to the power of minus 5x. This yields 63 alpha equals 3. Dividing both sides by 63 gives alpha equals 3 over 63, which simplifies to 1 over 21. Therefore, the particular solution is y sub p of x equals 1 over 21 times e raised to the power of minus 5x. Now, let us write the general solution. The complete solution is the sum of the homogeneous part and the particular part. So, y of x equals c sub 1 times e raised to the power of 2x plus c sub 2 times e raised to the power of negative x over 2 plus 1 over 21 times e raised to the power of minus 5x, where C sub 1 and C sub 2 are arbitrary real constants, determined only if initial conditions are provided. At this stage, our aim is to find the constants C sub 1 and C sub 2 in the general solution. The general solution is y of x equals C sub 1 times e raised to the power of 2x, plus C sub 2 times e raised to the power of negative x over 2, plus 1 over 21 times e raised to the power of minus 5x. We will use the given initial conditions, y of 0 equals 0, and the first derivative of y with respect to x at x equals 0 also equals 0. First, substitute x equals 0 into the general solution. Since e raised to the power of 0 equals 1, this gives y of 0 equals C sub 1 plus C sub 2 plus 1 over 21. But we are given that y of 0 equals 0, so we have C sub 1 plus C sub 2 plus 1 over 21 equals 0. Let us call this equation 1. Next, we differentiate the general solution to find the first derivative of y with respect to x. The derivative is 2 times C sub 1 times e raised to the power of 2x, minus 1/2 times C sub 2 times e raised to the power of negative x over 2, minus 5 over 21 times e raised to the power of minus 5x. Now substitute x equals 0 into this derivative. Again, since e raised to the power of 0 equals 1, we obtain y prime of 0 equals 2 times C sub 1 minus 1/2 times C sub 2 minus 5 over 21. But y prime of 0 is given as 0, so 2 times C sub 1 minus 1/2 times C sub 2 minus 5 over 21 equals 0. This is equation 2. This yields the following system of two equations, denoted S. Equation 1. C sub 1 plus C sub 2 equals negative 1 over 21. Equation 2. 2 times C sub 1 minus 1/2 times C sub 2 equals 5 over 21. To determine the constant C sub 1, we multiply equation 2 by 2 and add it to equation 1 to eliminate the constant C sub 2. This gives 4 times C sub 1 minus C sub 2 plus C sub 1 plus C sub 2 equals 9 over 21, which simplifies to 3 over 7. After canceling plus C sub 2 and minus C sub 2, we obtain 5 times C sub 1 equals 3 over 7. Dividing both sides by 5 gives C sub 1 equals 3 over 35. To evaluate C sub 2, substitute the value of C sub 1 into equation 1. C sub 1 plus C sub 2 equals negative 1 over 21. This gives C sub 2 equals negative C sub 1 minus 1 over 21. Since C sub 1 equals 3 over 35, we have C sub 2 equals negative 3 over 35 minus 1 over 21. The least common denominator of 35 and 21 is 105. Rewriting both fractions, negative 3 over 35 equals negative 9 over 105, and negative 1 over 21 equals negative 5 over 105. Adding these gives C sub 2 equals negative 9 over 105 minus 5 over 105 equals negative 14 over 105. Simplifying negative 14 over 105 by dividing numerator and denominator by 7 yields C sub 2 equals negative 2 over 15. Thus, the unique solution to the initial value problem is y of x equals 3 over 35 times e raised to the power of 2x, minus 2 over 15 times e raised to the power of negative x over 2, plus 1 over 21 times e raised to the power of minus 5x. Now, it's time to try it yourself with this homework. Solve this second-order linear ordinary differential equation. The second derivative of y with respect to x minus 4 times the first derivative of y with respect to x plus 3 times y equals 2 times e raised to the power of minus x. Find the general solution. Then, using the initial conditions, y of 0 equals 1, and the first derivative of y with respect to x at x equals 0 equals 0, find the unique solution. If you'd like, feel free to write your solution in the comments below this lesson 30. I hope you enjoyed this step-by-step solution. Keep practicing, share this lesson with your friends, and don't forget to subscribe to Math Olympiad Academy for more exciting math challenges. See you in the next lesson!